Hello and welcome back to another episode of Math with Sohn. Today we're going to continue AP Physics 1 by talking about Newton's laws of motion. Okay? So an important detail that you have hopefully realized by now is that we're in a new chapter, forces. And with forces, we introduce a new topic called dynamics. Dynamics is the study of motion and the forces it causes. Up till now, you've only been dealing with kinematics, which was the study of motion without forces. Now you have forces. Okay? So we have Newton's three laws, our main man, Isaac Newton. Newton's first law is the law of inertia, and the law of inertia indicates that an object at rest will remain at rest unless acted upon by some other net force. Okay, that is what you've heard of it. And the main thing is that objects resist changes in acceleration. They don't want to be moved. All right, things want to stay put, which kind of makes sense. People don't like change, nor does the rest of the world in physics, which is very unique because up until Isaac Newton had this, he flipped the script. Isaac Newton flipped the script. He was one of the first people that actually thought and flipped the idea that objects actually prefer to stay at rest. Every time before that, the theory was that objects preferred to be moving and stay moving. And that's not necessarily true. I don't know if you've ran for a while, but eventually you're tired of running. All right? Net force, when we're talking about these things, is the sum of all forces in a system. We need to do systems very soon and free body diagrams. That's going to be a different video. But if the net force, the sum of all forces, is a non-zero part, that means there is some sort of acceleration in the direction of that net force. So if you are moving somewhere, it's going to be accelerating. If you're not, it is not. So essentially, if the object is moving, some sort of net force had to have been applied. If there is no net force, then the object is in equilibrium and it is at rest and or moving at some sort of constant velocity. Okay, so if there is zero net force, that would indicate there is no friction or that the thing is just stuck in wherever a spot it is, then that would indicate that the object has no forces that are acting upon it out of equilibrium. That's an important detail as well. So if it were in equilibrium, for instance, if you decided to push very, very hard on a 3,000-pound boulder, it's not going to move. And that is because the net force that you are producing is not greater than the friction of that and the weight of that boulder, and therefore that object will remain at rest. Okay, you are pushing as hard as you can, but it will not move if you don't have enough force to do it, and you are at equilibrium with the static force of friction at that point. All right. Whereas if it is a tiny rock and you decide to kick it, that produced an acceleration, and there is some non-zero net force that you were able to overcome friction and gravity and other things, and that object will have accelerated in the direction of your kick. All right. Moving on to Newton's second law, we got Newton's second law, which indicates that force is equal to mass times acceleration. This guy, this is the end-all, be-all formula that you will need to utilize so often with Physics 1, okay? So what it does tell us is that we will have more force when we accelerate something more, which makes sense. It also tells us that the heavier that object is, the more inertia it will have, and the more force it will actually be able to produce. For instance, a rhino running at you will be a little more intimidating than a goat, because a rhino has a lot more mass. Doesn't matter if they're running at you with the same acceleration, they're going to produce different forces. The rhino might kill you, and the goat will probably scare you, but you'll be fine, hopefully. All right. To solve problems involving forces, you need to draw all the pictures of all the forces that are acting on the object. That would be known as a free body diagram. That's a different video. You would need to label each force, and you would need to apply the sum of all forces to figure out the mass times acceleration of that motion. Okay? With that in mind, the last and final Newton's law is going to be Newton's third law, which indicates that with every action, there is an equal and opposite reaction. For instance, if you decide, and this one's the weird one, every action has an equal and opposite reaction. Okay? For instance, if I decided to push down on this paper, and if you did this too, you could create a little experiment for yourself right here. Push down on whatever table or whatever surface is right next to you, and notice what you are feeling. Notice what you're feeling. I am feeling on the bottom of my hand the pressure of myself pushing down on the table. The table is pushing up on me with as much force as I am pushing down on it, which indicates to you that things that aren't necessarily thought to of actually be pushing against you in an opposite reaction are. All right? Energy cannot be created or stored, and we have to think about that when we're dealing with physics. All right? That's going to do it for this one. It's a quick one, short one. We're going to start drawing free body diagrams in the next one, which will enable us to solve these problems. I will see y'all in the next one. Bye.